In this video, I will discuss some NEET PYQs from the topic fluid dynamics. Fluid dynamics means the fluid is in motion. Fluid static deals with fluid at rest. These questions are based on continuity equation and Bernoulli's equation. First, I'll give some theoretical background. Continuity equation is basically conservation of mass applied to a fluid system. Consider this pipe. See, liquid is flowing. When we consider this section of the pipe between 1 and 2, the liquid is flowing in this direction, and we are considering steady state. Steady means things are not changing with time. So the mass of the fluid or liquid in this region between 1 and 2 should be constant, because this region, since it is steady, the mass of this region should not change with time. So that means whatever mass is flowing within this region through this section 1, Mn through section 1 should be equal to the mass that's flowing out through the section 2. Mass that's flowing out through section 2. And let me consider amount of time dt, small amount of time dt. So in this time, whatever is the fluid in this length of, say, v1 dt. v1 is the velocity of the liquid at this point, v2 is the velocity of the liquid at this point. Only the liquid in this cylinder will enter this region. That's easy to figure out. Consider fluid element here, will travel at a distance of v1 dt. I will cut this surface 1. Similarly here, the fluid element here will cut this surface, and the fluid element on this thing will just come and touch this section 1, and the fluid element just outside this dotted line will come up to here and will stop here. It will not cut the surface, because all the fluid will travel at distance v1 dt, and the height of the cylinder is v1 dt. So only the volume of the liquid within this cylinder of height v1 dt will cross this surface. Similarly, the fluid here of size v2 dt. v2 is the velocity of the liquid at this point. So the fluid element here or the liquid element here will travel at a distance of v2 dt and cut the section 2. And the one here will just come and touch this section 2. And the one which is here will come up to this point in the interval of time dt. So what is the fluid element within this volume will cross this section 2. So the mass inside this cylinder is density to volume of the cylinder. Density is ρ1, and the density of this at this section is ρ2, and volume of the cylinder is area of cross section A1 into the height of the cylinder is v1 dt. That should be equal to the mass that is crossing this section 2, that is volume of this cylinder into the density of the liquid at this location, that is ρ2. Mass is ρ into v, where ρ is density, v is the volume. So mass of this region is density in this region into the volume of this region, which is cylinder approximately, area of cross section, and height of the cylinder is v2 dt. dt will cancel. So ρ1 a1 v1 equal to ρ2 a to v2. So this is continuity equation, which is basically conservation of mass. Suppose you consider a liquid like water, where the density will not change. Water density here and here will not change. If it is gas, means it can get compressed and the density will change. But in case of liquid like water, density is constant, it will not change. So ρ1 equal to ρ2. In that case, the continuity equation will become A1 B1 equal to A2 B2. So when area is small, velocity will be high. So here the liquid will move with higher velocity. Since here area is increased, the liquid will move with lesser velocity. So this is V1 and this is V2. So this is continuity equation, which is conservation of mass. Next is Bernoulli's equation, which is conservation of energy applied to a fluid. So let me consider fluid flowing in a pipe like this. So let me consider the fluid in this region. Between section A and B. This pipe is a continuous pipe, so and let the water flow like this, or some liquid is flowing like this. So this is at a time, initial time T1. At a later time, the liquid will have come here and this thing will have moved here. See A prime and B prime. I'm identifying the fluid, liquid is region AB. So at T2, it will have moved here. So the energy of this identified fluid element will not change because energy is conserved. So initial energy equal to final energy, and the work done on the fluid will increase its energy. This work energy theorem, energy is conserved except for the work done. So since the fluid is moving up, height has increased, so we have to push the fluid. So some work is done on the fluid. So work is done on the fluid. And initial energy is energy of the liquid in the region A to B. And this final energy is energy of the liquid in the region A prime, B prime. Because AB has moved to A prime, B prime. And this EAB I can write as energy of the liquid in the region A prime plus A prime to B. This liquid from A to B I can consider as two parts, A to A prime and then A prime to B. Similarly, A prime to B prime I can consider as made of A prime to B and then B prime. Energy of the liquid in the region A prime, B prime, B plus energy of the liquid in the region B prime. So this and this are same, so they will cancel. So energy of this liquid and energy of this liquid are same except for the work done on this liquid. So here the pressure acting on the liquid is say P1, and here the pressure acting on this liquid is P2. So work done is force into area. That is force is pressure into area and work done is force into displacement. So this has made this much displacement. Let me consider small amount of time dt between initial and final states. So this distance will be v1 dt, and this distance is v2 dt. Velocity of liquid at this point is v2. Here it is v1. So this thing will become energy of the liquid A prime plus work done on the liquid equal to energy of the liquid in the region B prime. So this work done is force and displacement. Here the force is P1 A1 and the displacement is V1 dt. And here the force is P2 A2 and the displacement is V2 dt. But here the force and the displacement are opposite. So the F dot ds will be F into ds into cos theta. Theta is 180 degrees, so you'll have a minus sign here. Here the force and displacement are the same direction. Here the force is this way, displacement is this way. So there will be a minus sign between F in F dot ds. And energy of this liquid is, one is the, here is the earth surface. One is because of the gravitational potential energy. Another energy is kinetic energy, half mv square. So let the mass of this one be m1. So potential energy of this one will be m1 g h1. Let this height be h1 from the earth's surface, and the height of this one be h2. So potential of this one is mgh plus half m v square m1 v1 square plus this quantity p1 a1 v1 dt minus p2 a2 v2 dt. That's equal to energy of this liquid BB. That will be mgh of this element. Mass is m2 and the height is h2 plus half m2 v2 square. Only two forms of energy: gravitational potential energy and then this one. And let me assume the fluid is incompressible. In that case, this volume and this volume will be same. Volume of this one is A1 V1, area of the cylinder and the height of the cylinder. If the fluid is incompressible, then this volume and this volume will be same. And let me call this volume as dV. Both are dV. So dividing the full equation by dV, m1 by dV is rho 1 because density is mass by volume. So divide throughout by dV, we'll get rho 1 gh1 plus half rho 1 v1 square plus p1 minus p2 equal to rho 2 gh2 plus half rho 2 v2 square. So take p2 on the other side. So you'll get this result that for a liquid, p plus half rho v square plus rho gh equal to constant. P1 plus half rho 1 v1 square plus rho 1 gh1 equal to p2 plus half rho 2 v2 square plus rho 2 gh2. So that means this quantity at 1 and 2 is same. So this is basically energy. This is the potential energy mgh. For unit volume will be rho gh because mass by volume is rho. This half mv square, but for unit volume half rho v square. And this pressure energy for unit volume because work done due to pressure is P into dV. We just got energy unit of joules. So this pressure energy for unit volume dV is 1. So pressure energy per unit volume is P. So this way we can remember this relation: pressure energy plus kinetic energy half mv square for unit volume become half rho v square, and then mgh potential energy for unit volume will become rho gh. So with this theoretical background, we can solve these questions. Timestamps are given in the description box. You can watch parts of video if you're running short of time. I'll list some 3 questions. This is the first one. A wind speed of 40 meters per second goes parallel to the roof of a house. The area of roof is 250 meters square. Assuming that the pressure inside the house is atmospheric pressure, the force exerted by the wind on the roof and the direction of the force will be density of air is 1.2 kg per meter cube. You can pause and attend this question. So this is the roof of the house, and air is blowing like this at a speed of 40 meters per second, and the area of this roof is 250 meters square. Pressure inside is atmospheric pressure. Density of air is given. Okay. So basically, we have to find the pressure of the air here. Okay. So this air is coming from here in the same height. So later, it will be at rest when it is far away, and let the pressure be P, which will be same as atmospheric pressure, and the velocity will be 0. It will pick up speed, and then pressure will drop because according to Bernoulli equation, P plus half rho V square plus rho G H is constant. Pressure energy, kinetic energy, and gravitational potential energy. This rho G H will not change because of the same height. The wind is blowing parallel, so there is no change of height. So this is also constant. So P plus rho V square is constant. So far away, the wind will be at rest and the pressure will be atmospheric pressure. So as it moves, the speed will increase and the pressure will drop down. So we have to find the pressure here when the speed has increased to 40. So pressure here is atmospheric pressure and the velocity is 0 here, equal to the pressure here at this point, let me call it P2, plus half rho V2 square. So from this, I can get PA minus P2 as half rho V2 square. This roof here, inside there is atmospheric pressure, it's given in the question. Outside there is this pressure P2, which is less than PA. So there will be a net upward force. This pressure is more compared to P2. So the force on this roof is PA minus P2 into the area of this roof. PA minus P2 is this much. So force on the roof will be this pressure force into the area of the roof, that's 250 in SI units. Density of air is 1.2 SI units. So half into 1.2 into the velocity is 40 square into 250. So this is 0.6 into 40 square is 1600, and 250 can be written as 1000 by 4. 4 will go 4 times 400. So this will become, and 4 into 0.6 is 2.4. 100 and then 10 cube SI units. And the direction of force is upwards because atmospheric pressure is more. Here the pressure has dropped down because velocity has increased. So here there is some sort of a vacuum, partial vacuum. So there will be net upward force. B is the correct answer. So this is the house, and inside the house the pressure is atmospheric pressure, and outside the wind is blowing. Since the velocity has picked up, the pressure would have dropped a little bit. So this difference in pressure P naught minus P with the area of this roof is the force acting upwards. So to get the pressure here, I use Bernoulli equation. The energy here is P plus half rho v square, and the same will start from here far away with almost zero velocity. So the velocity will pick up and the pressure will drop. So here the energy is pressure energy P naught, which is same as atmospheric pressure, and the kinetic energy is zero. So from this I get delta P, which is P naught minus P, is half rho v square, and force is pressure difference into the area. Next question: cylindrical tube of spray pump, radius r, one end of which has got n fine holes, each radius r, small r. If the speed of liquid in the tube is v, the speed of ejection of the liquid through the holes is. You can pause and run this question. Draw a schematic diagram. So this is a cylindrical pipe, and here it's opening into n fine holes. So it's flowing like this, and it's coming out as a spray. This radius of this cylinder, this is a big cylinder and opening as small cylinders. So this cylinder has got a radius r, and this small cylinders has got radius small r, each cylinder, and there are 8 cylinders. So basically we can use continuity equation. So if you take a section here, the mass that's crossing this section is same as the mass that's coming out of this, all these small pipes. So mass is crossing this one is rho EV at this point. Rho, actually density is, it's incompressible, so density is same. So rho 1, V1, V1, this is section 1, and collection of all this is section 2, equal to rho 2, V2, V2. Rho is same, incompressible fluid, which they have not mentioned, but they should have mentioned, but we can assume it. This A1 is this area, it is pi r square into V1. Pi is there, pi will get cancelled, and this area is each one of this pi r square, and there are total n of them. So total area is n into pi r square into the velocity with which the liquid is coming out. V1 is given as capital V. So r square by n r square, V1 is capital V, is V2. So option A. E is the correct answer. So inflow rate of volume of liquid is equal to the outflow rate. So inflow is through the big cylinder and outflow is through the n small cylinders. This is the next question. Your fluid is in streamline flow across a horizontal pipe of variable cross section. For this, which of the following statements is correct? Option A, velocity is maximum at the narrowest part of the pipe and pressure is maximum at the widest part of the pipe. B, velocity and pressure both maximum at narrowest part. C, velocity and pressure both maximum at widest part. D, velocity minimum at narrowest part and pressure is minimum at the widest part. It's like a theoretical question. A pipe of variable cross section. So let me assume like this. Here the cross section is small, narrow end, and this is a broad end. E1, E2. We have this continuity equation for incompressible flow, which is E1 V1 equal to E2 V2. Actually, rho EV is constant. Rho 1 E1 V1 rho 2 E2 V2. If we assume it's incompressible, rho will cancel. So here the velocity will be more. Here velocity will be less. Narrow pipe will go fast. If the thing is broader means it will go slow. And Bernoulli equation energy conservation. So energy at this point, pressure energy, that's P1, kinetic energy half rho 1 V1 square. Horizontal pipe. So there is no difference in the gravitational potential. So that will get cancelled on both the sides. So leave out the MGH part, which is rho GH. P2 plus half rho 2 V2 square. So P plus half rho V square is constant. So if velocity is more, means pressure will be less. So here velocity is more, so P will be less. Here velocity is less, so P has to be more for the sum to be same. So velocity is maximum at the narrow part and pressure is maximum at the wide part. So option A, velocity is maximum at the narrowest part, it's true, and pressure is maximum at the widest part. A is the correct answer.